Swayam Prabha. Digital India. Educated India.
Welcome back. So, we will continue our lectures on solid propellants. Today, we will continue our discussion on the propellant ingredients. If you recall what we discussed in the previous lecture, that we started with the discussion on the fuel, because the common propellant ingredients are fuel, oxidizer, binder, plasticizer, curing agent, bond rate modifiers, and so on. There may be like more than 200 ingredients depending on the functionality of each of the ingredients they have been tried. Now, as I said earlier that fuel and oxidizer are the principal ingredients, because without fuel or without oxidizer the rocket propellant ingredient will not be complete, because only fuel is not going to burn, only oxidizer is not going to burn. So, it needs to have at least fuel and oxidizer. Other than that, it needs to have some binder, because we have to bind the solid particles. Oxidizers are mostly solid crystals. So, we need to have some binder which is kind of a glue type of glue which can bind the solid particles together, or the forming the fuel matrix. So, we started our discussion on the fuels. There are various fuels which have been considered or thought for solid propellants. The common one is the aluminum particles. So, these are basically spherical aluminum particles. Diameter may range from 5 to 60 micron, and they typically burn inside the solid rocket motor, and they form aluminum oxide. And since we said that metal particles are generally having higher energetic values, they provide heat to the they provide additional heat to the overall combustion, overall heat release from the combustion reactions, and the aluminum will become aluminum oxides. Now, as it proceeds towards the nozzle side, as the temperature drops, the aluminum oxides may become liquid, or if the temperature is low enough, the aluminum oxide particles may form into solids. Liquid oxide particles may become solid. That may be a disadvantages in the form like that some of the oxide particles may deposit on the inner liner of the chamber, or even in the nozzle portion. So, that may overall change the mass ratio of the rocket. Now, we also said that boron is also considered to be one of the promising ingredient as fuel, but the difficulty in burning boron in an efficient way within the reasonable combustor length, or within the given residence time of the combustor, it does not really have commercial applications. Although boron has been used extensively in order to see that whether boron can actually give the heat release in the combustion chamber. The other ingredients can be like beryllium, which is also thought to be the one of the promising fuel or metal particles, but the oxides of berylliums are very toxic. So, generally it is not considered, although the heating values are higher for beryllium as well. Now, looking towards the comparison of heating values of various fuels. Now, if you look at the comparison of heating values of aluminum, beryllium, boron, carbon, iron and other materials with in comparison with HTBB. So, HTBB is like rubbery substance. It is a polymer which is mainly used as a binder, but since it is a polymer, it can be used as fuel. And similarly, like paraffin wax is another fuel ingredients which can used as binder as well. So, if we compare the commercial polymeric fuel with the metallic fuels, you can see the beryllium has the highest gravimetric heating values compared to all others, whereas boron has the highest volumetric heating values compared to all other ingredients. So, in a sense, boron stands out to be the promising candidate in terms of volumetric heating values, because the aerospace vehicle, we said that it is a volume limited system. So, volumetric heating value high means it can give us, like, with the lower space we can actually pack more, with the minimum amount of the volume, it can produce higher energy density. So, it is like per centimeter cube or per meter cube. In that sense, boron stands out to be the promising candidate, but as I said, the efficient boron combustion is difficult due to its native oxide layer present on the particle surface. It inhibits its ignition and hence the combustion as well. So, the energy utilization is kind of difficult. So, if you look at the stages of boron ignition and combustion, primarily it covers with the boron oxide cell. Now, the liquid layer on that solid core boron exists once the temperature is beyond like 722 Kelvin, because the melting point of boron oxide is around 450 degrees centigrade or 722 Kelvin. So, the molten oxide layer is going to inhibit the oxygen reactions with the core boron particles. So, that is one of the drawbacks for boron particles ignition and combustion, and which actually inhibits its full utilization of energy. And once the oxide layer gets evaporated, the boron core boron is going to participate with the available oxidizer. So, these are the several stages of boron ignition and combustion, and due to this it requires some additional time to complete the combustion. So, for the given residence time, sometime it is not sufficient to complete the combustion of boron, and the full energy utilization is somehow not possible. Okay. So, I think we will talk about this metal particle combustion in a later part of this course, because there is a separate module on metal particle combustion. So, we will talk about that later on. This is just to give you some ideas about what are the different type of metal particles which are considered as fuels for solid propellant ingredients. So, in a nutshell, we can say that aluminum is a more common one, whereas other ingredients such as boron is also considered, but the utilization of boron's energy is still not harnessed, just because the difficulty in burning efficiently within the given residence time or the reasonable combustor length, whereas beryllium is discarded just because of the toxic nature of its oxide. On the other hand, if you look at the density of various metal particles like aluminum, beryllium, boron, carbon, iron, if you compare the density with the hydrocarbon fuels or the binder, let us say polymeric binder HTPB, you can see the density is almost of the order of like 3 times. If we see the aluminum's density is almost 3 times of HTPB. So, that way we can actually compact more amount of fuel mass within the given volume. On the other hand, the volumetric heating values of these metals are higher compared to the available polymeric fuel. So, in a sense, the metal particles can be utilized if we can somehow bind them within the given binder, and that can actually give us high performance in terms of like the ISP as well as the volumetric, as well as in terms of the density ISP, because the density here is quite high compared to the available polymeric fuel such as HTPB. All right. Now, as I said that the primary ingredients of the solid propellant are the fuel and the oxidizers. Now, there are different type of oxidizers which are considered for solid propellants. For example, like inorganic oxidizers and some organic oxidizers or explosives. So, inorganic oxidizers are mostly the solid crystals, for example, like ammonium perchlorate, which is considered as the common oxidizer for composite solid propellant. So, we will talk about the different types of inorganic oxidizers as well as the different types of organic oxidizers used for solid propellants. So, let us look one by one. So, as I said, the most common oxidizer is the ammonium perchlorate, which is NH4ClO4. These are basically crystalline oxidizer. So, they are basically crystal and they are of course inorganic oxidizer. Now, the ammonium perchlorate oxidizer has the high oxidizing potential and it is a preferred oxidizer due to its performance. Although we know that it is containing like chlorine atom within the molecule of the ammonium perchlorate. So, upon reaction it is going to produce like HCl. Although we know that it is hazardous for the environment as well as for the personnel who are working nearby, but still this is kind of a workhorse oxidizer for composite propellants used for solid rocket. So, it is kind of a preferred oxidizer since long because of its good performance, and we can actually maintain the quality, we can maintain the uniformity of the particles and of course, the availability. So, based on that the ammonium perchlorate is considered to be the most common or most widely used crystalline oxidizer. So, these are like a perchlorate based oxidizer. Other oxidizers can be like a nitrate based oxidizer, for example, like ammonium nitrate. The other perchlorate oxidizer can be like potassium perchlorate or sodium perchlorate, like we can show here. You see there are various other perchlorate oxidizer like ammonium perchlorate, potassium perchlorate, sodium perchlorate, and the respective molecular masses are given here. You see this is like 117.49, here is 138.55, here it is 122.44. Density also, of course, it is higher than the available polymeric fuel. It is always higher than the normal hydrocarbon density, which is of the order of like 900 to 920 kg per meter cube. So, generally they are denser than the polymeric fuel. Now, the oxygen content available in the molecule, it is already given here. For ammonium perchlorate is 54.5, potassium perchlorate is 46.2, sodium perchlorate is 52.3. So, depending on the availability, the performance, generally the ammonium perchlorate is the preferred oxidizers. The other oxidizers can be like ammonium nitrate. As you can see, the oxidizing potential is also kind of very high here, but there are some issues with the ammonium nitrate oxidizer or overall like where the performance penalty takes place, because this is kind of hygroscopic in nature. And because of the hygroscopic nature of the ammonium nitrate, it absorbs moisture and it changes its phases in the crystal. Sometime it may make it to some volumetric changes in the crystal as well. So, the hygroscopicity and the temperature deformation, like if we change the temperature of the environment due to some means, or if there is a change in the storage temperature, the ammonium nitrates actually changes its phases, and due to which there will be some void may be created within the crystal itself, which may lead to a problem in the performance later on. So, although ammonium nitrate based oxidizer has other positive attributes, for example, like it does not contain any chlorine atom within the molecule. So, it is not going to produce any kind of a reactive or hazardous products like HCl, because it is only contained the hydrogen, nitrogen and oxygen. So, it is in that sense it is environmentally benign, and also the oxygen content within the molecule is also higher, but due to the other issues like hygroscopicity and the phase transformation due to the effect of temperature, this oxidizer is not commonly used for high performing rocket, but for some medium performance and smokeless propellants where we can find application of ammonium nitrate. Of course, there are some modifications has been tried in order to improve the performance of ammonium nitrate oxidizers, like it is called PSAN or phase stabilized ammonium nitrate. Some amount of nickel oxide is added in order to reduce the change of phases within the oxidizer. So, the oxidizers are mostly the particles or crystals of various sizes, like as I said that here the ammonium perchlorate, they are used in various sizes. It can be like 600 micron, which is generally considered to be the coarser, or it can have like a smaller size as like 80 micron as well. But if the size is less than 40 micron, it is considered to be hazardous, because it can easily decompose or it can easily ignite in the storage location or even in the air itself, because this is kind of very much hazardous. It can sometimes it can lead to detonation as well. So, this is handled with care, but generally the mixture of two different sizes are used in order to improve the volumetric loading, because if you see there are some bigger crystals packed together, there will be some particular spacing will be present. So, in order to improve the packing, some small crystals are also mixed with this to improve the loading densities, okay, like this. So, in most of the occasion the bimodal oxidizers are preferred, like it is a mixture of two different sizes, one may be the coarser, another may be the finer one or the medium size. So, this is the common one. As I said, for the ammonium nitrate, the phase transformation take place. The ammonium nitrate it has some issues with phase transformation, and the phase transformation at 32 degree centigrade, it can cause about 3.4% change in volume, which is kind of significant, because if it creates some kind of a void within the propellant grain, that may lead to a big failure later on. So, this can actually change the this will lead to change in the physical and the ballistic property of the grain. So, this will very much influence or impact the physical and the ballistic properties of the grain. So, we must have to use this ammonium nitrate oxidizer very carefully by stabilizing using some nickel oxide or potassium nitrate, that will somehow lead to reduce the phase transformation, and that is why it is called PSAN or phase stabilized ammonium nitrate. So, even if it is used, it is used with some phase stabilization. Also, the moisture absorption is going to degrade the performance. So, that is another issue with ammonium nitrate. So, therefore, for high performing rocket, this ammonium nitrate is not preferred, rather the ammonium perchlorate are preferred oxidizers still now. Okay, so these are all about the inorganic oxidizers, but there are some organic oxidizers as well which have been used. So, what are the organic oxidizers? So, they are organic compounds with radical or other oxidizing fractions incorporated within the. So, these are like you can say organic compounds with NO2 radical. Very quick examples if we want to know are like the nitramines, they are the very common organic oxidizers. So, nitramines means we are talking about the HMX and RDX, they are considered to be like explosives. So, HMX is, the name is Har Majesty explosive, which is the chemical name is cyclotetramethynyl tetranitramine. So, you can write down the formula accordingly. It will be like C4H8N4NO2 4. So, that is the HMX is one of the organic oxidizer. Another organic oxidizers, or it is used as explosive also, which is RDX. This is also commonly known terminology. This is known as R&D explosive. So, instead of tetra, it contains like tri. So, its chemical name is cyclotrimethylene trinitramine. Okay, sometime what happens that if we added the RDX or HMX, they may they have the potential to react themselves. So, they are generally we need to add some amount of fuel or oxidizers in order to balance the materials. Otherwise, it is going to reduce the temperature or the ISP. So, when binders are added to HMX and HMX or RDX crystals, it is necessary to add another oxidizers like AP or AN, because these material can react and burn themselves when initiated with enough activating energy. But of course, at a certain conditions they may detonate it may detonate under certain conditions, but we have to remember that both HMX and RDX are stoichiometrically balanced. So, these are kind of stoichiometrically balanced. So, in order to improve the performance, or if you need to impact the temperature and the ISP, we have to add some amount of oxidizers or fuel to change the mixture ratio. So, whenever there is some binder fuels are added to hold the HMX or RDX in the matrix, it is necessary that some amount of AP or AN is also added. So, this type of oxidizers are having applications in a separate category of propellant is called nitramine propellant, and in fact, there is a modified version of the double base propellant where these type of oxidizers are used, and they are called composite modified double base propellant. So, once we talk about the category of propellants or category of solid propellants, we will talk about this HMX and RDX again. So, coming to the now these are like various oxidizers we have already discussed. Now, we have to remember that both the fuels and oxidizers, they are solid particles. So, we need to have some kind of a glue or some kind of a binding materials to bind them together, because only solid particles if we put, it is not going to form a solid propellant grain. If you recall what we had earlier, so it is already written here, the binder. So, if you recall in our previous discussion that inside the rocket we put one solid shaped mass, and by now we know the name, it is called the propellant grain. So, this is propellant grain, and as you said that propellant grain means it consists of fuel and oxidizers. So, let us say we have metallic fuel. So, metallic fuels are kind of some aluminum particles, let us say, and we have some, let us say, bigger size Ap crystals or mixture of bimodal Ap crystals. Let us say these are Ap crystals and we have like aluminum particles. Okay. So, how do you form these to the propellant grain if we just use the solid crystals? How do you form this? In order to give a structural glue or kind of a some binding, we need to, in order to bind the solid particles, we need to use the binder. So, you need to bind them using some kind of a binder, and they are going to act as structural glue, just like normal glue. It is holding all the solid particles and they are going to form this type of solid block of material, which is containing our fuel as well as the oxidizers. So, within this grain we are actually holding the solid crystals. Solid crystals are fuel and oxidizers. Okay. So, binder will act as the structural glue to keep this composite matrix bind together. Now, what are the different types of binders? Let us talk about that. So, binders are generally polymeric, pre-polymer or monomer. After we cure them and make it like grain type of, which once we make the solid fuel grains, so they become solidifieds. So, what is our preferred choice of the binder, because binder will also act as fuel. We have to remember that. We can write it here. So, if we recall from our previous lectures that heat of combustion, if we recall, in order to increase the heat of combustion, what we said, we have said that the heat of formation of reactants are supposed to be positive or small negative. This was our criteria from the heat release from the chemical reaction, because the heat release from the chemical reactions, we said this will depend on summation of the heat of formation of the products minus summation of the heat of reaction of heat of formation of the reactants. And from that analysis, we understood that the heat of formation of the reactants should be small negative or somewhat positive. So, the binders, since they are kind of like fuel, they are preferred if they have like small negative values of heat of formation. Okay. So, in that respect, we can preferred choice would be like simple aliphatic compounds, which can have like a very straight or simpler bond structures. But most of the aliphatic compounds like are having like methane, propane or butane, they are actually gases. So, gases cannot actually bind the particles together. So, we need to use some kind of a polymers which are basically cyclobutadiene, cyclobutadienes, that will kind of linear chain structure. They are called polybutadienes, and they will be like a many of them, like so there will be many of them form the chain structure, and this will form the butadiene groups. So, these butadiene groups will form the polybutadienes, and they can be ends up with like either hydroxyl or carboxyl. Depending on that, there are different types of butadienes like hydroxyl terminated polybutadiene or carboxyl terminated polybutadienes, but basically they are the polymer which is going to provide the structural glue for the grain. So, they are providing the structural glue to hold the solid fuels plus the oxidizers. Remember, both the solid fuels means we have the aluminum particles or even boron particles, and the oxidizers are basically ammonium perchlorate or ammonium nitrate. They are the solid crystals. So, the polymers are going to provide the structural glue to hold the solid fuels and oxidizers. Now, there are different types of polymers which have been used as binder. The very common one is called hydroxyl terminated polybutadiene, or very commonly it is known as the HTPB. You may actually find it in many literature that HTPB is used as the common binder for composite propellant. For example, like the booster stage where we need to launch the vehicle. So, the first stage, which is the solid propellant rocket, is generally having the binder as the HTPB or the hydroxyl terminated polybutadiene binder. Okay. There are other binders. So, I think we will talk about those type of binders in the following lectures, all right. Like the end of the polybutadiene may be with carboxyl terminated, instead of hydroxyl it can have like carboxyl terminated. So, we can have it like it is called CTPB. There are other binders like it is called polybutadiene acrylic acid acrylonitrile, which is PBAN. So, we will talk about that binders briefly in the following lecture. Okay. Thank you.